moving to the higher positions. 2s, okay? Actually, they stay here with a little bit higher, okay? You have a 2s, 2p. And then the 2p have the same, but they have to fulfill this one, this one, this one, after go back. Okay, the rule will be explained to you after. Okay, so in normal state or in ground state of an atom, this one will be the most stable electron configuration or the most stable state of energy. Okay, it means the atom will prefer to separate or set the electron stay in the orbitals with that energy, okay, or the lowest possible energy state. Okay, this is the most stable state of the electron configuration. And this one will say to you another information. This one only the most stable state. This means that the electrons sometimes can stay in the lower stable state. Okay, in the lower stable state, or we call the excited state, not ground state anymore. This means that some electrons from the lower energy levels orbitals will jump to the higher one. Okay. So for examples of electron configuration, this one is a way for you to write down a sentence. You don't have to draw a diagram like this anymore. Okay, so the lithium atoms have 3 electrons like this. So now you will have 1s, 2s, 2p, something like this, right? And in the case of lithium, you have to fulfill 1, 2 electrons in 1s first because of they have a lower energy levels. Okay, and after that you fulfill 2s. Okay, so let's help me to remember. Sometimes I write here a full around with 2 sides, okay, of the head of around. But sometimes you will see the electron will be represented by a half around like this, only one side. Okay. So by that way, you will see 1s now will be fulfilled with 2 electrons, and 2s will be fulfilled with only 1 electron. Okay. So now we will write down the electron configuration of this one is 1s2, with 2 here is the number of electrons inside that orbitals. This orbital here is 1s, okay, 1s2 and 2s1. Okay, this is a way to define or write down the electron configuration. And actually you were introduced quite clear about this in high school, right? So about the nitrogens, for example, you have 7 electrons on nitrogens. Okay, so similar to that guy will have 1s, 2s, and a little bit higher 2p. So when you fulfill the electron into the nitrogen, you have to fulfill this one first. Okay, 1s first. After that, you fulfill 2s, and then you move into 2p. So 2p can be write down like this: 1, 2, and 3. But let's imagine 3 orbitals of 2p, this one, this one, this one, have the same energy levels as I write here. Okay, so if you have 1 electrons to fulfill or to move in that 2p, they will prefer the first orbitals, of course, right? But when you have the second electron move in, do you think that they will fulfill this guy? No, they will not prefer that orbital anymore because of the orbital now contain 1 electron. Okay, so the space for the second electron will be less, will be smaller than the second one and third one. So the second electron will prefer to move in the second orbitals of 2p because they have the same energy levels. Okay, and you continue if you have one more electron with that energy levels. Okay, they will prefer to fulfill the third orbitals. Okay, just to disperse the energy. Okay, or they will disperse the areas in which the electron can move around. Okay, and now when you have more electrons move into that orbitals, okay, the set of orbitals, now they will continue to fulfill the first one because they don't have any other place. They will choose any one of three orbitals with one electrons here to move in. So we will write this. The next electron will jump here, and the next electron will jump here. Okay. So this one is said to you about the Hunt rule or Hood rule. Okay. This one is namely that they generate orbitals or orbital with the same energy. Okay. This guy say that to fulfill the orbitals. Okay. In the lowest energy state will be attained when the number of electrons with the same spin is maximized. Okay, as when I write before. The p orbitals, the first electron will jump here with a spin of +1, for example. Okay, so the second one, the second electron will prefer to jump here, the second orbitals, to increase the spin. Now you have a spin of 1, right? After that, they move here to increase the spin one more time to 1.5. Okay, and then when you have more electrons, now they don't have another orbital with the same energy to move in, so they have to move here. They continue to jump in this position, but with the Pauli principle, that electron will not have the same spin with the first one, so they have an opposite spin. Okay, the second one too, and the third one. Okay, so it is a way for you to fulfill the electron into the box diagram. Okay, in which you follow 200 rule. Okay, electron will fulfill in the degenerate orbital, so that the maximized spins will be reached. Okay. So as you see, 1, 2, 3 electrons will jump here for the structures of nitrogens, and then you can write down the electron configuration of nitrogen is 1s2, 2 electrons, 2s2, and 2p3. Okay. So this one is several electron configuration of light elements from lithium to sodium. Okay, with a total electron jump move from 3 to 11. Okay.
Excuse me.
Yeah.
Can you draw the orbital diagram of the oxygen atom?
Of the oxygens?
Yeah, and fluorine atom.
Okay. So any other place, easier place? So okay, let's consider I writing in another colors. Okay, let's consider no electron here for the case of lithium. Okay, I will write this one for the oxygens. Okay. So how many oxygens in the how many electrons in oxygens?
8.
8, right? So you have to write down 1s with 2 electrons like this. Okay, 2s with higher electron levels will be like this. Okay, 2p follow to the whole rule before. You have a 1, 2, 3. Okay, so now you see 2p of nitrogens. This guy will have a one more position. Okay, still have a more position to get one more electrons. So When you have 8 electrons, they will jump here. Okay, this one is also the box diagram or orbital diagram of oxygens, and the electron configuration of oxygen will be 1s2, 2s2, and 2p4. Okay, for the case of fluoride have 9 electrons, right? So this one become 1s2, 2s2, and 2p5 with the one more electron stay here. It's okay?
Okay, thank you.
Okay, welcome. Okay. How to build electron configuration of atoms. Okay, so now you will have a diagram like this, or the diagonal rule. Okay, you see that in this direction, or sometimes you can use the reverse direction to represent for the energy. This one energy is going down with this direction. Okay, in normal case. So 1s, 2s, 3s, we go from this way. 1s first. After that, we continue in this 2s. We continue in this 2p, and then 3s. Okay, and then moving in this way 3p, and be careful because in the energy diagram you see in the very first line of today, 4s have a lower energy than 3d. So you after 3p, you continue with 4s before moving to 3d. Okay, and then continue with 4p, 5s, and then move back in this direction. Okay. Okay, so this one is the right for almost kind of atoms, for almost atoms, of almost elements, but except some of specific case like copper or chromium. Okay, the copper and chromium, they have a 9 electron in d orbitals. Okay, so for example here, the copper, they have a 9 electron in d orbitals. Okay, you can imagine this one. I will write only 3d. Okay, that orbital will have 5. How to say, subshell will have a 5 d orbitals, and moving this way you have a 4s. Okay, normally when you write, you will write like that. Okay, so this one we have a 2s, 4s will be fulfilled by 2 electrons first, because the 4s have lower energy than 3d, and 9 other electron here. Oh, sorry, let's write in the right way. And they lack of 1 electron in the last position. Okay, so in the case of copper, now you will see a state that 1 electrons from 4s will move to 3d, and now you will have electrons in 3d is fulfilled. But what 4s have only 1 electrons. Okay, this one is specific case and similar to the case of chromium. In the case of chromium, you have okay, 1, 2, 3, and 4. This guy have a 2 electron in the first state, and the chromium has the same things. Electrons will jump here, okay, to fulfill this, and no more electron in this position. Okay, there are we call this one is a specific state. Okay, and this one can be explained by when you have as you see that in the case, you have 1, 2, 3, 4 electrons. Now 5 electron of 3D, sorry, 5 orbital of 3D is get electron in 4, and only one have no electrons. So they led you to a thing that these orbitals will be lack of electrons. Okay. So in that case, they prefer to get one more electrons from 4s to fulfill it, okay, to avoid the degenerate of energy of the 3D. Okay, actually 3D and 4s have a very similar energy levels. So that kind of the structures with lack of one electron in d orbitals, we prefer that the kind of elements we prefer to get one more electron from 4s, move in to fulfill d orbitals. Okay, as you if you read deeper in the book, we will see that actually the 3D have how to say, even they have the energy levels is higher than 4s, okay, but the size of the electron of the orbitals and 4s will be quite similar. Okay, so the movement of 4s to 3D to fulfill that orbital to avoid the degeneration of 4D of the d orbitals is frequently, and it's very simple. Okay, for the other, for examples, is the case of the guys they before chromium, for examples, they have only 3 electrons. Okay, so now you have a 3 electron with 3 orbital with 1 electrons and 2 other empty. It's not a big problem because of now the space of the the space that contain electrons and no contain electron or empty is now not so different. Okay, but in the case of 4 orbital get electrons and 1 more empty, now you have a very small space of no electrons, so they will let degenerate in terms of energy, and the element they don't like this, and they prefer to get 1 more electron from 4s to fulfill that orbitals. Okay, so let's have me to remember the copper and chromium, okay, for 3D. And actually, this concept become quite complicated since you move to the next guy, like 4D, like 5D or 6D. The orbitals or the elements here, they sometimes will not show that rule. Okay, they will not show that specific case. Okay.
So, is there any general rules? Are there any general rules regarding this? For example, are there any general rules regarding this?
Can you speak louder? Can you speak louder?
Okay, okay. So, are there any specific rules regarding this? For example, an electron from the s orbital can
You mean you want to know the rule for this?
Yes.
For this movement?
For the example, an electron from the s orbital can go over to fill the group of degenerate orbital from the left.
Okay. This guy, Mr. G, is saying on the chat box, and I have the same idea. Okay, I have the same comments. There are no rule for this one. Okay, in the case of 3D, we see it, but in the case of 4D, we no see it. Yeah, it's irregular. Okay, so you have to remember this case. If you have to write down the actual configuration of copper or chromium, you have to remember this. There are no rules for the movement. Okay? It's okay. So now, just Mr. Hainam. It's not for all elements. For example, it's work with 3D9, 3D4, okay, for S2. This one will become, oops, sorry, no place, 3D10 for S1. And this guy will become 3D5 for S1. But the case of 4D9, 5S2 is not work like that. Okay. So in that case here, sometimes it will become more complicated since the size of the orbital increase. Okay. Now the movement of electron is more complicated, and we can say sometimes we can call it a kind of entangles. Okay. So the movement is, or the transition of electrons is now become very complicated in the case of 4D. And if you continue to 5D, I'm sorry, so now you have an involvement of 4F2. So it's become much more complicated. Okay, so let's remember in the case here, for 3D, there are movements, but 4D, 5D is not the same. Okay, and in another thing, I forget it, the leader. Okay, what's happened? I forget one more thing. Okay, so even you write down, you see the 4s, okay, have a lower energy level compared to 3D. Okay, but normally in configuration, electron configuration, you still write 3D before 4s. Okay, so you can write down like 3s2, 3p6, 4s2, and then you fulfill the electron here. It's okay. Okay, so now the examples. The actual configuration of silicon 14. Okay, now you have a 14 electrons in silicon atoms. So you have to fulfill the state 1s2, 2s2, 2p6 is now you have a 10 electrons, right? 3s2 and 3p2. Okay, this guy is fulfilled by the right way. Okay, but in the case of B, you have 1s2. Okay, it's right. 2s1, and now you see the 2s1 have a lower energy than 2p. So this means that the electron on p orbital should not be fulfilled before the full electrons of 2s get or the orbital of 2s get full electrons. Okay, so you have to get 2 electrons on s before you move into p. Okay, so this is the trouble, and this one is wrong, this one is right. Okay, in the case of B of bosons, you have the same thing. 2s get lack electron, but 2p have electron, so it's not happen. And then you always have a 2 electron on 1s fulfill, 2 electron on 2s fulfill before moving to 2p. Okay, it's the way for you to continue to write down the actual configuration of any elements. Okay, so the question leads you to another thing. Let's consider the case of silicons. They have 2 electrons on p orbitals. Okay, the case of bosons have 1 electron on the 2p's of p orbitals. Okay, so you led you to a case. If you have a silicium crystal, silicium or silicons, let's consider something like this. And in the case, they are changing by 1 bosons. Okay, so now what's happened? Now you see Now you see the silicium stay on 3p, right? Oh, sorry, 3p. Borons, electrons stay on 2p. Okay, and they have a lower 1 electron compared to silicium. Okay, so when you replace one or silicons by one boron, normally this position have a silicon, right? And now we replace them by one boron. So now you have a state that 1 electrons from silicium, 3p, right? A little bit higher energy levels compared to 2p. So you will have 1 electron from, I will change the colors again. 1 electron from silicium we prefer to move into borons. Okay, so in that case, you will see silicium now or silicon now will lack 1 electrons and become silicon plus. This guy will contain a positive charge. This one contain a negative charge. Okay, and in case that guy become positive, now you will have another movement of the next, okay, of the next silicons. You can consider you have some other movement too. Okay, so in that case, you will give the movement or movement of the positive charge from silicons to another silicons, something like that. Okay, so it means that now the silicon structures or silicon crystal can have an ability to transport a positive charge. Is right? So that phenomenon is namely p-type silicons. Okay, and this one is important in the case of silicon solar cell. Okay, it's what happened in silicon solar cell. Okay, silicon solar cell will contain a p-type silicons and also one n-type silicons. In another case, n-type silicon is mean that you will dope or you will replace the silicon by another elements which have a higher numbers, okay, or more electrons than silicons, and the electron will be jumped to the silicons. Okay, we call this one n-type. Exactly, thank you, Chi. So by that process, they will let the movement of charge inside the silicon crystal. By that way, you will let that material from insulator to become conductors. Okay, or we enhance the ability of the silicon to transport electron. It's okay. So is it something similar to? No, it's not similar to the case of semiconductors, but it has to increase the ability of transport electron of silicon crystal, and it's very important in terms of silicon solar cell. And now you know that actually we have some other technique for the solar cell, but silicon solar cell is one of the most common see. When you go to some of province in the middle of Vietnam, you will see some of the solar cell field there, like in Bình Định province or Ninh Thuận province. Okay. So silicon technology here, as you see, okay, as I said to you before, you use people use boron to make silicon become p-type silicons, right? And they also use another thing like arsenic or phosphor with electron or with the higher electron number compared to silic to donate electron to silic. Okay, so by that way we generate n-type silicons. The word p and n here is say to you the positive and negative. Okay, you have a positive type of silicon and negative type silicons, and when you combine them together, now you will have an ability to separate then electrons and hole with positive charge generated by the solar light, okay, in the structures of silicon. Yes, Kiet is right.
While we consume phosphorus to silice, it is anti.
Yes, I agree
Yeah.
with you. I said that when you have a boron in the silicon crystal, you have p-type, right? And in the case you have a phosphor or accent, you have n-type silicons, okay? And p-type and n-type is the two compartment of the silicon solar cell. Okay, thank you. Okay, so it's the examples how you use the electron configuration to explain some properties of materials, right? In another side, this one, or as I said one time for the tutorial class, the set of the elements here is named the B groups of the periodic tables, or we can consider them as the transition metal. So transition metal here is what? Is a kind of element with the last electron stay in the d orbitals, or sometimes we will call them d block elements. Okay, so there are several types of very interesting columns. Okay, for example, this one, copper, silver, gold. Okay,
It is a good conductor.
yes, of course. So they are a good conductor because they show properties of electron cloud. Okay, and this kind of metal will conduct electron very easy. It's totally different with the silicons. Okay, so there are a set of the elements with similar properties. Okay, like the case of copper, silver, or gold. You see sometimes copper is silver, and gold. They are quite soft metals. Okay, they have a quite low oxidation capability. Reduction capability. Sorry, and then you will see that they are making. They can be very easy to perform some kind of jewelry. Okay, it's very soft metals. Some other thing you see, like the case of this column, nickel, palladium, platinum. Do you remember several kind of the reactions, like a hydrogenation reaction in the organic chemistry, as you see in the high school? You do the hydrogenation of alkane, okay, to alkane, okay, by the hydrogenation, okay. So that hydrogenation can be catalyzed by the presence of palladium or platinum, right? But you also can use the nickel for the reaction. So you will see this element, the element in that column will show similar properties. Okay. In the other case, this guide, a lot of metals here we are working on. Okay. So for example, molybdenum or tungsten. So molybdenum sulfide or MOS, there's no place to write. Okay, this one can catalyze the reaction of water splitting, as we are doing here. Okay, water with H2O will be separated into H2 and O2. So it can be catalyzed by MOSX, and the very funny thing, and MOS2 too. Very funny thing that tungsten, we kept that you here, sorry. So you have the same WSX, WS2, we show the similar property for the catalytic activities of the water splitting reaction. Even they have the same structures. No, I will not say that. Okay, the word catalyst is quite a funny thing. We can predict some material can be catalyst for some reaction, but in most cases you cannot see it. You cannot predict it. The research on the catalyst is the try and fail. Okay, and the thing is the catalyst for lignin or cellulose to arene or alkanes, as you say here, now is still a very interesting topic for the research of the chemist. Okay, actually it's very hard, and normally in this moment they still have no industrial scale of this research. Even we know that we have a lot of cellulose or lignin, right? But we still cannot transform them into the very high additional or how to say additional qualified materials. Okay, there are a lot of research focused on this one, but still have a very lack or very few commercial application of the catalyst. Okay, a second please. Okay, so you see, is this one is beside the what I said to you before. Now we can conclude that the chemistry, or we see that we cannot conclude. Molybdenum and tungsten, they stay in the same column, right? They're quite identical. So you can see in nature, molybdenum enzyme sometimes can be replaced by tungsten enzyme. Okay, for example, the xanthine oxidase family, sulfide oxidase family, or dimethyl sulfoxide reductase family. Okay, you can replace this one with molybdenum by tungsten sometimes. In another guys, the 8B. Okay, 8B is a group of several elements with the electrons stay in the position of 8, 9, 10 in 3D, right? Iron, cobalt, nickel. This one have a similar properties, not same. Okay, or the combination of them become a very interactive or a very interesting for our life, as you see here. Okay, some of the enzyme, actually many enzyme, they have a bimetal centers like this, iron and nickel at the same times. Iron and nickels. Okay, iron, nickel. This one is only the explanation or the examples of the hydrogenase enzyme. Okay, or iron in this case. Sometimes you will see some other kind of enzyme who contain iron, molybdenum, or iron cobalt. Okay, so they show a very similar properties, or they can combine to work in an organic system. Okay, so in the last part, this one is just a kind of story. And now, in the last part, you are knowing a diagram. Okay, you're knowing about the box diagram of the electron configuration. You know how to write down the electron configuration in normal way. It's okay, but you see, in the periodic table or in nature in general, there are some of the elements like neon with electron is full fill. Okay, electron is full fill here. They become very stable elements. Okay, and as you see, neon or argons or kryptons, okay, or helium, they will be named noble gas or the inert gas. Okay, decay of gas represent to a very stable electron configuration, and then you will use, in the case of condensed writing, you will use the configuration or electron configuration of noble gases to shorten the other elements. Okay, so in the case of normally we will use the electron configuration of the closest noble gas, the smaller noble gas. Okay, closest smaller noble gas, to write out or to shorten the elements, the electron configuration of the other elements. Okay, for example, you have a neon is a noble gas, sodium is a little bit bigger compared to the neons, and neon is the closest one for sodium, right? So now you have an electron configuration of neon like this, electron configuration of sodium is only one position or only one orbitals different compared to the neons. So now you can write down here, neon in the square bracket and 3s1. Okay, so that way it helps you to shorten down the electron configuration writing of the other elements. Okay, we call this one condensed writing. Okay, so now let's move to the periodic tables. The periodic tables. So the periodic table, as you see, in before this guy, very famous guy, Mendeleev, right? People just know there are several kind of elements, but they are not have a, they are trying to set them in the table, in a box, but they cannot. They can set them in some of several similar properties. Okay, but they cannot explain why they have a similar property like that. Okay, so in the case of Mendeleev, in this moment, he based on the similar properties of the elements and they set them in a tables. So we call this guy periodicity of chemical properties. Okay, and based on the Mendeleev, in the case of Mendeleev, we still lack of many elements in the periodic tables because of Mendeleev. At the time of Mendeleev, we don't have enough technology to define the other elements. Okay, so he have several elements. He based on the periodicity or periodic properties of chemical properties of the elements, and they set them in a table with some of the empty position and wait for new elements. Okay, so at this moment, at our time, actually it's around 100 years ago, the people they can define that now when the elements having a similar electron configuration, they will have a similar properties. Okay, the cost of periodicity or the similar chemical properties, okay, or the circle movement of the chemical property of elements is the repetition of the similar electron configuration. So what is the similar electron configuration? Let's see. For example, element with similar electron configuration or electronic structure of the outer shell. Okay, this one is namely valence shell. Outer shell is that guy. Okay, the electron or the orbital in the outermost shell of the electrons, of the element, sorry, of the atom, sorry. So this one is namely valence electron. Okay, and the other part, normally we call the inner electrons. Okay, so when they have the similar valence electrons, you have 1s1, 2s1, 3s1, 4s1, 5s1, and 6s1. Okay, so this guy will be set in the same column. Okay, so when you open the periodic tables, now you will